Hello. After finishing our discussion on lattice vibrations, now we shall discuss about magnetism. We are aware of a bit of the magnetic properties of materials. Some materials are diamagnetic, where if we apply an external magnetic field, the material develops a magnetization in the direction opposite to the external magnetic field. And of course, the magnetization is weak. There are paramagnets, paramagnetic materials, where the magnetization is induced in the direction of the external magnetic field, but it's pretty weak. Then there is ferromagnetic material. Ferromagnetic materials, if an external magnetic field is applied, then develop a strong magnetic moment along the direction of the magnetic field. But even if there is no external magnetic field, it may have some magnetization in its ferromagnet form. Not all ferromagnetic materials are magnets, but there are magnets that are made of ferromagnetic materials. There are also antiferromagnetic materials. Antiferromagnetic materials have spins in the system that are opposite in orientation, opposite to each other, and that makes it antiferromagnetic. So ferromagnetic, antiferromagnetic, these two are long range orders of spins in a particular material, and this order takes place in a certain, up to a certain temperature, not at any arbitrarily high temperature. There are also ferrimagnets. Ferrimagnetic material are just like antiferromagnetic material, where the spins are oppositely aligned, but then not all spins are of equal length, something like this. That's ferrimagnet. It's also a long range order and survives up to a maximum limit. Diamagnetic and paramagnetic materials, these properties survive up to very high temperature. So let's start our understanding with diamagnetism and paramagnetism. Magnetism is a completely quantum phenomenon. It's inseparable from quantum mechanics. For a strictly classical system in thermal equilibrium, it cannot display any magnetic moment, even if a magnetic field is applied. So what contributes to magnetism? The first thing that contributes is the spin of an electron. Electrons have spins that has only quantum mechanical origin. There is no classical analog to it, and this contributes hugely in the magnetic properties of materials. Then there is orbital angular momentum of an electron. and finally the change of orbital angular momentum due to applied magnetic field. If we consider magnetization and denote this with capital M, that would be the magnetic moment per unit volume. And then we can define another quantity called magnetic susceptibility. Which is expressed with chi is given as magnetization over the magnetic field in CGS units, and in SI units it's given as mu naught times the magnetization over the magnetic field. These are the expressions for the susceptibility, magnetic susceptibility. Now let's understand Langevin's theory of diamagnetism. We want to find out how diamagnetism appears, and we will first go through the theory that Langevin developed in this. Langevin's theory is rather a classical theory. Diamagnetism is associated with the tendency of electrical charges to partially shield the interior of a body, of a material, from an applied magnetic field. What do we mean? We mean if an external magnetic field is applied on a material, then the material itself tries to somewhat shield, that is insulate, minimize the effect of the external magnetic field inside the material. Hence comes diamagnetism. So when we try to understand the diamagnetism, then we consider the atoms and ions. They employ Larmor theorem. That means in a magnetic field, the motion of the electrons around the central nucleus is, at least to the first order in the magnetic field, the same as a possible motion of the electrons in the absence of the magnetic field, except for the superposition of a precession of the electrons with an angular frequency. That means because of the application of external magnetic field, the electrons precess, and this precession is with a frequency omega, which is given as E electrons charge times the magnetic field over twice mc. C is the velocity of light. This is in CGS unit. This precession happens to obstacle the external magnetic field, and in SI unit this is given as EB over twice m. If the field is applied slowly, the motion in the rotating reference system will be the same as the original motion in the rest system, before the application of the field. The average electron current around the nucleus is initially 0. The application of magnetic field will cause a finite current around the nucleus because all of the electrons are moving in the same direction. The current is equivalent to a magnetic moment, but this time opposite to the applied magnetic field. And it is considered that the Larmor frequency that we have got the expression here is much lower than the frequency of the motion under the central field. The Larmor precession of Z electrons is equivalent to an electric current. So the current is I equals charge times the revolutions per unit time. Which is, the charge is given as minus ZE, Z is the atomic number, times 1 over twice pi EB over twice m in SI units. So the magnetic moment, that is mu, of a current loop is given by current times the area of the loop. The area, if we have a radius rho of the loop, then the area is given as pi times rho squared. Then the magnetic moment mu would become minus ZE squared B over 4m times rho squared average. This is of course in SI unit, and in CGS unit mu can be expressed as minus ZE squared B over 4mc squared times rho squared average. So we are considering rho vector in a plane. We can call it xy plane. That means rho squared average can be given as x squared average plus y squared average. This is the mean square of the perpendicular distance of the electron from the field axis passing through the nucleus. The mean square distance of the electron from the nucleus is given as r squared average. This quantity is x squared average plus y squared average plus z squared average. And if we have spherically symmetric charge distribution, then we can write x square average equals y square average equals z square average. And if we have that, then we can clearly write r square average equals 3 over 2 times rho squared average. So after doing all these, we can find out the diamagnetic susceptibility per unit volume as chi equals n mu over b. Mu is the magnetic moment, equals minus n z e squared over 6 mc squared r squared average. This is in CGS unit. If we write down the equivalent in SI unit, we will get chi equals mu naught n mu. Mu naught is the free space permeability, mu is the magnetic moment, one must be careful about this, over B equals minus mu naught n z e squared over 6m r squared average in SI unit. And this is the classical Langevin result.